I guess I don't need to announce homework, that homework 2 is due today. Some of you, those of you who are not here probably know it. And there might be some correlation to that. I do want to remind you that there's a midterm next week in class, same time, same week, no, same time, same day and all that stuff. And we are covering everything till whatever I do today. Okay? Yes?
I have a question about the homework. I posted this on the forum, but for the second question of the experiment, we're asked to determine value for R and U that gives like the best accuracy. And the data that we're asked to use, I always have 100%.
In that case, it's uses, and that actually does happen even in real data. Not 100%, but you get the same cross-validation accuracy for different choices. At that point, it's a fine loss. There's nothing you can do. You just pick random. Oh. Go ahead.
Oh, so on the third question, there's two like data folders, right? Data 0 and data 1.
Yeah.
Are we supposed to run the perceptron, the regular one, on just data 0 and then a margin on data 1, or
No.
all of them on all?
So every algorithm you run on every data.
Oh, okay.
Yeah. And that's how you generate all the plots. I saw you first and come back to you after.
Yeah, go to, I forgot my question.
Oh.
You're distracted easily.
Thinking about what I actually got, I was noticing that the basic perceptron was not very accurate, whereas the margin perceptron was very accurate. Is that to be expected?
Yes. In general, when you have noise in the data, the margin perceptron tends to do better. So typically my experience has been margin perceptron beats perceptron and averaged margin perceptron beats everything else.
So are we supposed to cross?
Okay.
Sorry, no, go ahead.
You might forget again.
Yeah, exactly, I was thinking. So are we supposed to cross validation, or it seemed like it was optional, yeah?
It is technically optional.
Okay.
If you do use it, I won't complain. If you don't use it, follow some systematic procedure to find the hyperparameter and write what you did.
And then the other question, is it more, the focus of question 2, is it more about plotting the versus the different dimensionality, or is it more about finding the best kind of the best hyperparameters? It seemed more oriented towards kind of.
So I want you to basically, okay, so the goal of that question is really to, wait, which one's 2 again?
Is that 2?
Oh, I meant 3.
3, yes.
3.
Yeah. So the goal of 3 is really to figure out what happens to the perceptron algorithm as dimensionality increases.
Okay.
I think of hyperparameter choice as part of the learning process. So you pick some hyperparameters, you run your learning algorithm, and you get some result, and you plot that. So really, in some sense, the motivation behind this question is for the perceptron algorithm. We've seen that the mistake bound is R square over gamma square, and we know that R is a function of the dimensionality. So as the dimensionality increases, you expect the perceptron algorithm to do worse after the exactly same number of iterations. Does that happen or not? In either case, what in the report, I want you to explore possible reasons for whatever observation you make.
So the number of aspects that we use should be held to a constant.
Just report it to a constant.
Just 10.
If it says 10, 10. Yes.
Okay, one question is, so the set of graphs, we have to have one set of graphs for each folder? Or
Yes. Yes. So you'll have,
that will be a total of 8 graphs?
if you're a graph student, yes.
Yeah, okay.
Yeah, so one homework 0 and 1 will have each one 2 graphs for each algorithm. And
So there's 2 graphs for each algorithm, right?
2 graphs for each algorithm for
And one set for each folder, so that's
okay, this is too complicated. Let's just pick an algorithm you'll get 2 graphs for data 0 and 2 graphs for data 1.
Cool, so 4 graphs per algorithm, right?
Yes.
So 8 graphs in total.
For one more thing, can the number of cross validations that we do affect, like, impact the results? Like, can it skew it?
What do you mean by number of cross validation?
Like, you know, if you split the data into 10 sets versus 5 sets.
Oh, I see. In practice, the most, you're talking about when you do k-fold cross validation, the k. Do you want to do 3-fold cross validation or 5 or 10-fold cross validation? It's less sensitive to that. Most of the time in the literature, in papers, people pick a number and just, nobody questions that number. You just need to do cross validation. Typically, I've seen 3 and 5. Or sometimes I see 10. Very often that choice is decided by how much, by your, the time you have really, by how much processing power you have. You've been holding up your hand for a while.
For the plots, so it's 2 per thing, can you have basically 2 for data 0, and 2 for data 1, just overlay, like the aggressive,
Okay, so the main concern is that whoever is grading it should be able to understand what you're doing.
Okay, so as long as they can understand that.
Yeah, I don't really care about the actual plot, but it should be understandable, and please don't plot it by hand. Or that's it. I mean,
Okay.
you need to make it. You need to make it legible, understandable, and all the curves that were demanded should be there.
Okay.
So you said that perceptron does it, margin perceptron better, and average margin than the best. What about the?
What about aggressive?
Yeah.
Aggressive sometimes works better. The jury is a bit somewhat out. So in some sense, aggressive tends to might overcompensate, but not always. The jury is out.
So just to make sure I understand, when we're doing it on all those, so for each folder there's 10 different data sets, we should tune the algorithm for each one of those data sets, yeah?
Yes.
Okay,
Yes.
independently of the
Yes,
other
yes.
data sets.
In fact, the general recommendation, not just for the homework but in life, is if you change a feature, you do cross-validation again. If you change the learning algorithm, you do cross-validation again. If you add a feature, if you remove a feature, you do cross-validation again, because that counts as a new problem. So for every training setting, every time you have to produce a new set of parameters, and if you have changed any inputs to the problem, you have to do cross-validation again. That's the best case situation. In practice, what happens though is you don't have that much time. So you do cross-validation on one reasonable setting or two, and you notice that the hyperparameters that are chosen, basically the best hyperparameters tend to be the same, and so you say that we expect it to be the same and you move on. That's a little less optimal, but sometimes in the interest of time that works. Was that? Yes.
Should we keep updating when we're running through the test data?
Absolutely not. There is a distinct, at least as far as the homework is concerned, there is a distinct train phase and a test phase. And the model gets updated during the training phase. At the end of the training phase, the model is fixed and it's frozen, and you never change it after that. And this is, in fact, we'll be talking about that a bit today. This is the batch setting. You're given a training set, and you have to pick the best classifier you can based on that. And you never get to change it after that.
You mentioned before that you would have a practice midterm available.
Yes, it should show up either late tomorrow or early Saturday.
Thank you.
As with cross-validation, is there going to be much of a performance change if we, say, try and find the best R over one run versus over a batch?
That's actually an excellent question. Yes and no. I can't say for sure.
Okay.
One thing that is often done is you find your cross-validation, the best hyperparameters for using fewer epochs than the total number that you will eventually run. With the hope that if you run, say, 3 epochs, irrespective of what the thing would converge to after 10, after 3 you might be able to tell the difference between the hyperparameters and the relative ordering won't change. That's the hope. And people do that a lot, again, as a way to save time. Yeah. There are other questions? Yes.
So I've done the same thing. I did the cross validation for one epoch and used the hyperparameters in the batch perceptron.
Yeah.
And it gave me really poor result for the high dimensionality data.
Yes. There are no guarantees with that. It can happen, and it's often a way to, instead of one, if you feel like exploring this concept a little bit more, try it for a few, not 10 but 3 or 2. See if it changes. Like I said, there are no guarantees. Okay, excellent. All good questions. If there are no other questions, let's move on to the rest of, or let's move on to a new topic. Starting today, and certainly continuing after the fall break, we're going to be spending a few weeks on computational learning theory. And this is one of my favorite topics in machine learning. This is the theory of machine learning. And you may not have noticed it, but we've already been doing some theory of machine learning, and we'll continue. This is basically the formalization of a few ideas that we've been looking at so far. Just as a checkpoint, where are we? We are exploring supervised set learning, where we have instances and we have concepts which are just functions that can predict, which can classify these instances. And the concept is hidden from us, and so our goal is to use a training set to find a hypothesis. And the device that explores the hypothesis space is called a learning algorithm. It uses the training data to search through the hypothesis space and find the best one. Once that's done, once training is done, then we can now take this classifier that we have. I use the word hypothesis and classifier interchangeably. So we take the classifier that we have and we let it run wild on future examples. We've looked at a few learning algorithms. We started off looking at decision trees, we looked at nearest neighbors, and then moved to classifiers. In particular, we looked at 2 of them, perceptron and winnow. So these were just algorithms. The more fundamental machine learning ideas that we looked at are not really, even though I introduced these as related to certain classifiers, these are ideas that pervade across, that should influence your thought when it comes to machine learning. One of them, which is very, very dominant, is the idea of representing objects as high-dimensional vectors. And then there's this problem of overfitting. I'm not going to say much more about this right now because we'll be spending some time talking about overfitting. There's the curse of dimensionality, which should generally be in the back of your mind and should make you uneasy. And then the fundamental question here is, what is learning? There are many ways of asking that question. There are many ways of answering that question. And one way of answering that question is mistake bound. We defined learning as some algorithm sees examples, and eventually, as it keeps seeing more and more examples, it stops making mistakes. So, and under the mistake bound model of learning, we looked at 2 practical algorithms, perceptron and winnow, which can actually give fairly good classifiers. Are there questions about where we are or what we have seen so far? This is like a 1-slide summary of about, 4 weeks. Yes?
Beforehand, you talked about blowing up the dimensional space and at the same time talked about the curse of dimensionality.
Yes.
Will we ever talk about how to blow up a dimensional space?
So, how to, what do you mean?
Like, are there certain procedures to go through?
Okay, we will get to that probably when, around the time that we talk about kernels. We will get to that. Most likely it will happen in the second half of the semester.
Okay.
If there are no other questions, let's go on to the lecture on learning theory. So, obviously I'm not going to cover all of this today. In fact, my hope is to just finish the first topic and start talking about the second one. So I'll tell you about what does it mean, what do we expect from a theory of learning or a theory of generalization, and start talking about this idea called probably approximately correct learning. Eventually we'll give a formal mathematical definition of learning and use that definition to explore some positive and negative results. Some things can be learned, some things cannot be learned because they are computationally impossible or they are information theoretically impossible. And then I'll talk about this fantastic idea called agnostic learning, which is probably the general theory that covers real world learning situations, and we'll get into other topics like we see dimensions and stuff probably 3 weeks from now. So let's get started on this journey. I'm going to, when I say theory of learning, really what I'm thinking about is how can I trust that the classifier that this algorithm produces is going to be good. In fact, what is good, and are there some functions which are more amenable to being learned than others? In general, I like to think of these as just the laws of nature. I mean, there are laws of nature for physics, and physics is really the study of laws of nature, and computational theory is the study of the laws of nature, quote unquote, when it comes to learning. What we care about, what we want, is some theory that can relate the various pieces of the puzzle. So what are the pieces? First of all, there's a set of functions. There's a set of functions that the learning algorithm has to search for. Under the assumption that learning is search for functions, there's a set of functions that the learning algorithm has to search for, and this is the hypothesis space. If that set is big, then learning is hard. If that set is small, maybe learning is hard, we don't know. So the complexity of the hypothesis space is important. Another one is, we are never going to see infinite data. So we are going to get a finite number of examples. So clearly, the number of examples must be an important attribute when it comes to talking about whether a function can be learned. If I give you too few examples, then it seems like learning should be impossible. But not just the number of examples, but also the way in which the examples are presented. We saw one way in which examples can be presented, which is the online setting, where the learner gets to see one example at a time. Perhaps will this change if the learner gets all the examples up front and does more? The two new things that and these are things that we've already seen. The two things that are different here are the first and the fourth items in this list, which is, let's talk about the fourth one. There is some concept, there is a function, a hidden function, and if I give up any hope that the true function can ever be perfectly learned, then I have to start thinking about error. So another piece in this puzzle is how accurate can that function be, can the hypothesis be when you compare it to the true function. So, and the final thing is the probability, which is in this list the first item, the probability that you're going to find a good enough classifier. Now that's a very complicated concept, and I'm going to introduce this as we go along. So to get started, let me pull up an example that we've seen before, and in fact this will be an example that I'm going to have for the rest of almost all this lecture. We're going to be studying this tiny little toy problem because it introduces a lot of interesting aspects that we care about. So we care about how good is our learning algorithm, and suppose I tell you that the true function is a conjunction. Not only is it a conjunction, it's a monotone conjunction, meaning it's a function that looks like f on top, The true function is assigns a value true when x2, x3, x4, x5 and x100 are all true. If any of them are missing, then the function will say false. That's the true function. And there is some source that has given us examples. So nature or teacher has gone out and labeled, has applied this function to a randomly chosen set of points. Just to remind you, I use 1 in this case, for at least for this thing, I use 1 to represent true and 0 to represent false. So a bunch of examples are chosen from the wild, from just randomly, and this function is applied to them, and we see pairs, we see examples and their label. So the first row on top there is the example that is all ones, and the function f is applied to it, so its label is 1. So we get a finite data set. In this case we have some 8 or 9 examples. One way, and we've already seen this before, to learn this concept is called elimination, and we'll stare at elimination a bit more. And what elimination does is simply get rid of all examples that have a label false. Look at only the examples that have whose label is true. If all these examples have a label true, then all the features that are in this example must be relevant. Take the intersection of those things, and that's it. Every feature that occurs in all the training examples which are labeled 1 should be relevant. Put them all into a conjunction, and that's your final function. That's what's predicted. That's the output of the learning algorithm. It just so happens that this output, in this data set, the final hypothesis that's learned is not exactly the same as the one that we as the true concept. So f was the true concept. It did not have x1, but it just so happens that in the training data, whenever the output was 1, x1 was also true. So the hypothesis that was learned contains x1. So clearly the function that's learned is not the same one, and the question that keeps people up at night is it good enough? How do you know that this hypothesis will be okay? Is it okay, first of all? Yes?
Seems like the same problem that statisticians face to say, is your data that you're making statistics on representative of the population?
Yes. So now that's a good observation, in fact. Let me repeat that. It's the same problem. Effectively, the question boils down to, is the data that I have chosen, or not I have chosen, the data that is given to us representative of the true data that exists?
Depending on the number of samples, you can argue that the likelihood of it happening is x1 occurring is relevant to one of the other key features. So you can argue, given that you've done a large amount of samples, that is good enough.
Alternatively, that's kind of what you said is a bit more complicated, because but it's actually the right direction. There are two ways of analyzing this. One of them says, every time I saw a positive example, it had x1 in the training set, and maybe the training set is representative, which means in the future, whenever x2, x3, x4, x5 and x100 are there, x1 will show up as well. So what this means is, I thought I had a typo there. What this means is that the probability that we will see this kind of an anomalous data point where x2, 3, 4, 5 and 100 are around but x1 is not around in the future has to be low, because we've seen so much data, so many examples where x1 was always tagged along. If the future behaves like the past, then x1 will continue to tag along. If that is the case, then we can probably be successful. And continuing this line of reasoning gives us the probably approximately correct framework of learning, which is the theory of learning. and I see that both of them are numbered 1, but that's probably because both are equally important. The other version of answering this question is something we've already seen, the mistake-bound learning. So far, I have not seen any example where x1 that contradicts the hypothesis that x1 is in the conjunction. So I'm okay. The next time it comes in, I'll fix my hypothesis, I'll make one mistake, and I'll be okay in the future as well. So another way of analyzing learning is how many mistakes have we made? And this gives us online learning. So the mistake-bound learning is one theory of learning, and as I said, it basically just counts the number of mistakes before learning converges. It's a good model because it's practically useful. Very often data comes in a stream and it models many interesting situations, except the problem with the mistake-bound model is it makes absolutely no assumptions about how the data is presented, about the distribution. It makes this adversarial assumption. In fact, it assumes that let's pretend that the data stream that we get is the absolute worst possible sequence of examples as for this concept. That's a good thing because if you are able to do the worst case well, then everything should be okay. But it's also a bad thing because it seems like we are missing out. Is the worst case going to happen? Should we not account for the fact that data comes from a certain distribution? The data has some regularities. And following that line of reasoning gives us the pack learning. So pack is a model for batch learning. And batch learning is the following setting. You get, and this was exactly the question that was asked before, you get a bunch of examples, training examples, you give it your learning algorithm, give all of them to your learning algorithm. The algorithm does something with it, and that's it. It does not get to see any more training examples. It produces a function, and that function is fixed, it's written in stone, and it's out there and deployed in the wild. So you don't get to change your classifier after you finish your batch. The batch can be huge. You can have 1 million examples, but that's all you get. Now, in this setting, the question that's really important is not how well we do during training, but how well we do on future examples. Because once training is done, we don't get to modify our classifier anymore. So the only question that's important is how well does this function that's written in stone approximate the true classifier? Questions? Yes?
I'm just wondering, I don't know if you've already addressed this, but why don't we continue to modify our classifier when we see real data or test data?
Mostly, well, 2 reasons. The somewhat more, the weak reason is that it lets us do the math better. But the real reason is when we actually deploy the classifier in the wild, we never get to see the true data, true label. So pretend that you've written a classifier that, let's say, classifies tweets as spam or not. You go out there and hire a bunch of people and manually label tweets as spam or not, you get some good, clean data. You get 1 million tweets that are labeled, and you apply your classifier out in the wild. How do you get labels for that? There is no gold data.
So then, I'm thinking about, I think it was Wolfram Alpha recently released a algorithm that you can drop a picture in, and then it tells you what's in the picture, what's in the picture, and then you can give it feedback. You can say this is, so what kind of algorithm is that?
Oh, that could be, that setting is semi-supervised, most likely. There is probably a fixed training data set. The classifier has been learned on that. And then, the user gives feedback, and based on the feedback, the classifier gets perhaps the user gives, actually I take that back, it's not semi-supervised learning. Potentially what they do is they collect all the examples that come in and then retrain their classifier.
So it's like they have a secondary classifier that has more training data?
Yeah, probably the more training data is noisy because who's to say that you're not an adversary? You're probably a competitor for Wolfram Alpha which wants to bring it down, so you keep giving it bad data. So it's noisy, so there's no guarantee of that data, so they don't. So as you go along through the semester, one thing that I really want to push, one idea that I want to push is that labeled data is probably the most valuable resource that you can find. we live in the world of big data, but it's really big unlabeled data. Labeled data is expensive, hard to get, requires experts, and it becomes harder to find labeled data. So you have to come up with tricks like this, where we kind of rely on weak, possibly adversarial, and see if we can do something. Okay, yes?
I was just gonna say, so how do you test unlabeled data? Like,
So you can't. There is no way of testing unlabeled data. So what you do is you hold out some part of your training data that you pretend is an approximation of future, and you never see that except maybe once or twice. You never let your classifier touch it. You don't see it because you might end up contaminating your classifier, and you evaluate on that. Okay, so now that hopefully the batch setting is clear, let me also just formalize this setup a little bit more. We have instances, and this slide is going to very quickly get filled up with a whole bunch of letters representing different things, so let's step through. There are instances. There's the instance space, which is a set of all possible examples. Think of it as a set of all possible names in our batch classifier. Or in your homework, the instance space for the 10-dimensional setting is all possible vectors of size 10. There's a concept space. The concept space is a set of functions. The concept space is a set of functions from which the true classifier could have been chosen. We hardly ever know the concept space because we don't even know what the true function is. So it's just this hypothetical object that we seek to find. The object that we get to control is the hypothesis space. The hypothesis space is a set of functions, a set of classifiers that your learning algorithm gets to explore. Our hope is that the hypothesis space at least contains the concept space, because only then can you contain the true function. Okay? And I'll use H for hypothesis space. In the batch setting, we are given a training set. Now, the training set is a finite set of examples that are drawn from X, from the instance space, and the true hidden function f is applied to all those examples, and that's all we have. This is the only interface between the true function and our learning algorithm. What we want is a hypothesis, one member of the hypothesis space, such that for every possible example, h of x matches the true prediction, f of x. Question to you guys. Do you want a hypothesis that matches matches the label for every example on the training set, or do you want a hypothesis that matches every example on the instance space, every label on the instance space? In other words, would you be happy if you find a hypothesis such that h of x is equal to f of x for every x in the training set, or would you be happier if you found a function which is such that it's true for all x?
Well, the second one implies that.
The second one implies the first. Yes, that's a good observation. But we only get to see s. We don't get to see x. So would you be happy if this situation happens? Can you think of a counter example where it can happen and still will fail? Overfitting, but specifically think of one example, a trivial classifier, which is always correct on the training set.
You have a training set of one that has true.
I give you a training set. It's always correct on any training set.
Just record the training set.
Exactly. The classifier is called a table. You put your training examples in a table, and then when a new example comes in, you look up thing on the training set, you look up the particular row and produce the output. That's going to get 100% accuracy on the training examples because you're really not doing any learning. So, what the thing to note is that training examples are generated according to some process. There is a fixed, we are going to assume, and this is the first important assumption that we are making in our journey towards PAC. We are going to assume that there is a fixed probability distribution, I call it D, over the instance space. And examples are sampled according to that distribution. And this distribution over the instance space never changes. And what we want eventually is we are going to evaluate our classifier on more instances that are drawn from the same probability distribution. Questions? What does it mean to say that there is a fixed but unknown distribution on the instance space? You had a question?
Yeah, exactly. It's like I was asking, what do you mean by drawing according to the distribution?
So for example, let's say that your training examples are points from, are vectors in 2 dimensions. So points from the plane. There is some, or in fact, let's make it even simpler. Your training examples are 1-dimensional examples. So it's a number. You have only one feature, and it's a number, and there is some, which means I can draw it on a number line. This is x, the same x as this. And there is some distribution on this space. It may be fixed, unknown, and weird. And drawing examples means this point here has a higher probability of getting chosen than say this point here. You randomly sample respecting the probability distribution on the instance space. This is 1 dimension, but I can expand this to arbitrary instance spaces. Yes.
I mean, you're going to try and have more examples representing things that have a higher probability?
Yeah. Yes. That's exactly. Yes. We're not going to try to do that. We are assuming.
So that's what magically happens?
That's the underlying assumption that we are going to make. There is some fixed and unknown distribution. The important thing is it's fixed and it's unknown. We don't care what the probability distribution is. All we care about is that it's sampled. The data set is training set and future examples are drawn from the same distribution.
So that is like if you drew them all perfectly randomly, then you should naturally represent the...
Exactly. And also in the future, the examples will respect that distribution as well when we are testing. You first and then you.
So is the distribution same for all dimensions?
No, what do you mean?
The probability distribution.
I don't understand.
The probability distribution from which we'll be drawing the example from a distribution, from a dimension.
No, so it's not, the word dimension, the dimensions have nothing to do with this, because think of the probability distribution is not factorized according to the dimensions. Every point in the space is assigned some probability. So that particular combination of, we are making no assumptions about the problem. In fact, you know what, we're making no assumptions. That's a strong assumption that you're making there, and we're not making that. It's some probability. We don't know, we don't care. All we care about is that it's fixed.
So does it follow from there that,
Can you repeat that?
so does it follow from this setup is that whenever that example is at very extreme of a mean, that it's always there's always going to extrapolate poorly. Is that what you can say? Or it has a very high probability of
That's, I agree and disagree with you, because let me try to restate what you said in a way that's more acceptable to me. Examples that have low probability of happening, we don't mind if the classifier gets them wrong, because they are not going to happen very often.
Just to clarify, so H, the hypothesis space, is a subset of the concept space, which is a concept of all
Superset.
functions?
No, the concept space is some set which we don't know, we don't care. We are hoping that the hypothesis space contains the true concept. That's it, the one function that we care about.
Oh, H is a superset of C.
Yes. we are hoping. In practice, it's not going to happen. In fact, dropping that assumption takes us to agnostic learning. We'll get there in 2 weeks.
What does it mean that the probability distribution is fixed? Fixed with respect to what?
With respect to any, what do you mean? It never changes. It's a probability distributions are functions, right? That function never changes. Meaning,
If you run it again, it doesn't change?
oh no. There is this is the probability distribution that generates data, that generates
I see.
instances. There is some process in nature which generates instances, and that process is basically, that process follows the same probability distribution over time. It
So
never.
if you're pulling more training data instances,
Exactly.
then you're going to get out of the same distribution.
Exactly. That's the right way to think about it. Remember that this is an assumption that we don't make for the mistake bound setting, for online setting. We don't even, in the online setting, we assume that it's the worst possible distribution. Here, we are relaxing that assumption by saying, I don't know if it's relaxing, we are saying that it doesn't have to be the worst, but whatever it is, it's fixed. Good questions. So, moving along. And we've covered a bit of this already, so let me just. So, this assumption of fixed distribution is very important. One, and it's important for 2 reasons actually. The first one is what I said earlier. It gives us hope that the future will be like the past, and our only, but the learning algorithm's only connection to the concept function is through past examples. So if the future is like the past, then there's hope that it will be able to learn the function. Without that assumption, then it becomes harder to even make any formal statements. If the true distribution keeps changing, then we are going to be, it's possible that we'll get hurt in terms of accuracy. The second reason why this is interesting is because, and I'll get to that in a bit, once we fix this distribution, even though it's unknown, we can give it a name. We'll call it D. And now I can start defining the error and accuracy in terms of this fixed distribution. I don't know what the distribution is, but I can still reason about it. And start, we can rely on what we know about how probabilities behave to make analysis, to analyze algorithms. In the context of the previous, the tiny little example that I had, assumption of fixed distribution basically says there's some process that generated the training data, and there's this one feature, and let's call it this bad feature x1. It occurred in every training example. Because the probability distribution, that the process that generates examples is the same, with high likelihood, x1 will occur with positive examples even in the future. Why? Because that's pretty much how we've got these 8, in this case 8 or 9, but we've got these million examples that say where x1 always occurs with positive examples. Then the probability that x1 does not occur with a positive example has to be low, because we've got enough samples that seems to suggest otherwise. So if it is low, then maybe it's okay, because we will make errors on those examples, but they happen so infrequently that it's okay. This intuition lets us build or formalize this definition of error. The error of a hypothesis So the error of a hypothesis is, we can use this fixed unknown distribution to define the error of the hypothesis as we have 2 functions, f, the true function, and h, the hypothesis. And the error is simply pick a random example from this distribution, and the probability that these 2 functions will disagree on this randomly chosen example is the error of this function. What I mean is, we have some instance space, this box here, and remember that the functions are basically, or binary classifiers are basically functions that take some subset of this instance space and say they are labeled plus and the rest of them are labeled minus. So let's say this is the set of points that the true function, the true concept, f labels as plus. And we get some finite sample subset of this, the training set, and let's say our classifier has learned a function h, and let's say the function h labels this other circle as positive. Now there are two regions where these two classifiers disagree, and what we define as the error of the hypothesis h is basically the volume of those two regions, but not the volume, but the weighted volume, because we are weighting it by the probability. What is the probability that a point gets chosen from here or from here? That's the error of h. Questions?
So this is like two experts with different opinions.
Well, one of them is an expert, F. H is just trying to mimic.
Oh, I see.
Yeah, H is the pretender.
Right.
Okay. So in an ideal world, we would like to measure the error of the hypothesis, and I'm going to call that error D. This is the generalization error. This is called the generalization error or the true error. In an ideal world, we would like to measure that and control that, and that if we are able to bring it down to zero, learning is perfect. Unfortunately, we don't live in an ideal world, so we cannot compute that quantity because we can't even enumerate all examples in the instance space. So what we have to live with is something called the empirical error. The empirical error is an estimate of the true error. We have a finite set of samples, S, and we can measure the error of the true function on each of those, the error of the hypothesis on each of those functions, and take the average. That's the empirical error. And if you remember your probability class, so the law of large numbers says if you have enough examples, counting the empirical error will give you an estimate of the true error. Questions? And in fact, by the way, what you are measuring in your homework is basically empirical accuracy. You have a finite set and you are measuring what's the accuracy on that. What you are hoping for is that it gives you a representative of the true accuracy. Now, yes.
So when you see examples afterwards, and they are coming in at a different, it appears to be a different distribution than what you trained on, can you do something about that, or can you set up flags to say, hey, maybe we need to retrain?
So this is actually a hot area of research. It's called domain adaptation. We do not know the correct answer to that yet. That's an open question.
Because in statistics, you can do something like, what's the probability that this data came from this?
Yeah, but for that you need to not only learn the true function, but you also need to start learning, estimating the probability, the distribution from which the data is drawn.
Right, I'm just saying,
Yeah.
like you can approximate your distribution from your
Right,
test
and
data.
typically
And then if your input data afterwards
comes from a different one, then you probably try.
With like a certain p-value comes from a different distribution, then you could raise some flags and say,
Variants of
maybe-
that idea are basically used to solve domain adaptation.
Domain what?
Adaptation. Alright, so we have these two ideas, the empirical error and the true error, and now we can start talking about overfitting in a slightly more formal way. Overfitting happens when the empirical error on the training set is more than the generalization error of the function. So empirical error of a function is more than the generalization error of the function, then the function is said to overfit. Why? Because you have a small set of examples and you're getting very low error on that. If I said more, then I was wrong, I meant less. If the measured error on your finite set is less than the true error that this function can get, then your function is not good, because you are doing very well on this training set but not so well on future examples. So the classifier that we spoke about a bit before, this classifier that just remembers examples wildly overfits, because it gets zero empirical error. It perfectly remembers all the training examples, but it has no guarantees in the future. So under this setting, we can redefine batch learning as batch learning is simply this style of learning where our goal is to find algorithms that avoid overfitting. In other words, we are given some finite training set and we want to find functions that are not fooled by that finite training set, that are not fooled by the fact that we only have a finite number of examples and yet is influenced by it, because remember that our finite, so we have two competing goals here. On one hand, this finite set of examples is the only source of supervision that we have with respect to the true function. We know nothing else about the true function except what this training set tells us. So that suggests that it's good to get a classifier that predicts these examples correctly. On the other hand, we don't want to overfit. We want to find a function that does well on the training set but not too well. Questions? So let me just quickly do this comparison of batch and online learning. We've seen online learning before, so it's good to contrast how what the differences are. In online learning, we make no assumptions about the way in which data is presented, in which we don't care about how examples are produced, because we are going to assume the worst case. In batch learning, we make an assumption. We assume that examples are generated from a fixed and unknown distribution, and this distribution is over the instance space. The mode in which learning happens is different. The method in which examples are presented to the learner is different. In the online case, the learning algorithm gets examples in rounds. It's like a game, one at a time. The learning algorithm gets an example, it makes a prediction, and perhaps it uses the current example to correct itself and moves on. In the batch setting, the learning algorithm gets a training set that's drawn IID from the distribution. IID it stands for independent and identically distributed. This is important, and this is the assumption that lets us get basically that drives all the math. Every training example is drawn from the same distribution, so they are all identically distributed, the distribution D, and they are all independent, meaning the first example does not influence the second example. So no example influences each other, and basically they are all just randomly and independently sampled from the same distribution. This assumption of IID is at the heart of basically all of this style of analysis. The third big difference is what we care about, what we seek to quantify. In online learning, our goal is to in the mistake-driven version, our goal is to bound the number of mistakes over time, because we have this infinite stream of examples and we are happy if the learning algorithm stops making mistakes. In the batch setting, our goal is to find an example that has low generalization error. It has a low probability of making mistakes, provided examples were generated in the same way. Questions? Yes.
IID again, independently.
Independent and identically distributed. So one example of an IID process is, say I have a coin. I don't know its bias. Let's say, I don't know. Let's say it has some probability of getting heads. The probability of getting heads is some p. I toss the coin once, I see heads. I toss the coin twice, I see heads again. I toss the coin 10 times. These 10 tosses are all independent from each other because none of these tosses influence any of the others. And they are identically distributed. They are all tosses of the same coin. So we are assuming a similar thing about training examples. You draw a training example from some distribution and you draw it again. You draw another example and these subsequent examples don't, or no example influences the choice of another one.
And we're assuming the same thing for the online learning?
No, in online we are making no assumptions about, there is no distribution. It makes no assumptions about distributions. In fact, we don't care at all about how examples are presented to us. Other questions?
That confuses me because it seems like we do care, right? That's why we shuffle each epic because.
Oh no, oh good. This is, I'm glad you asked that question. In the pure version of online learning, there is no shuffling, there are no epochs. You run your perceptron algorithm, let's say you're talking about perceptron, there's an infinite stream of examples that keeps coming in. And that's it, we don't care what, there is no shuffling, there's just one loop. This version of doing, the version that you're implementing, the multiple epoch version, is actually the batch version of perceptron. That's a good point actually. So, if you were actually implementing perceptron in the purely online setting, there are no epochs. You do one. There is no even. It's not even right to say there's one epoch because the assumption is that examples keep coming in, and there's this mysterious process, possibly adversarial, that keeps generating examples. Other questions? Right, so we have 20 minutes and I'm going to just introduce the idea of probably approximately correct learning by analyzing a simple, so I'm going to introduce it through an example. We're going to do some math and we're going to analyze that elimination, the elimination algorithm, the trivial little algorithm that we saw, and derive a bound. It's a toy analysis just to give you an idea of the kind of math that's coming up. So we'll analyze this simple algorithm and get some, basically prove a theorem about it and generalize this to, or then most likely not in this class but in sometime later, I'll get to a definition of this PAC algorithm, of what it means to be PAC. PAC stands for probably approximately correct. And then it turns out following this PAC style of learning gives us a mathematical definition of Occams Razor. Occams Razor simply says, I need to find keep it simple. You need to find a function that is as simple as possible. And Occams Razor basically jumps out of the PAC style of analysis. So that's, jumping ahead, let's talk about learning conjunctions again. Same data, and now I've written down the elimination learning algorithm. What you do, so in fact, what you do is, you first discard all negative examples because they are going to teach us nothing in this algorithm. And then you build a conjunction that consists of features that are available in every positive example. It's called elimination because every positive example, if a feature does not appear in a positive example, that feature gets eliminated. If a feature does not appear in any positive example. So for example, this. So in the middle, the 0, that positive example eliminates that feature because here's a positive example, and yet where this feature is 0, where this feature does not occur, and yet the label is 1, which means that feature is not relevant. Because we are assuming there's no noise. We are still playing this sort of a pretend game where we assume this noise-free universe. Now, I want you to notice that clearly this function h that is produced is consistent with the training data. It will correctly predict the label for every training example. Right? Is that correct? Following this algorithm will give us a consistent hypothesis. Now, it's consistent, but sadly it's not right. Because there's this x1 that just tagged along with all the positive examples, and it was not in the true function that's on the top. x1 came along and it just happened to be there with every positive example. Let's now try to think about when can this x1, how much can this x1 that's around, that's there but shouldn't be there, how bad can it be? To think about that, the first claim that I'm going to make is that any hypothesis, any function h, like the h here, that's consistent with the training data, will never make mistakes on negative examples. Why?
Because one of the other ones that should belong are going to be false. So the conjunction will predict it correctly.
Right, exactly. That's the right answer. But did you also have to say something?
I was just going to say, like, you could visually think that if you have a function h that's consistent, it's got to be like a larger conjunction. So visually, like, if you think of it as
actually the smaller. It's a smaller.
Yeah, it's contained within the larger.
So the one way of thinking about this is, let's consider positive and negative examples. What is a mistake? A mistake on a positive example can happen only if this function h, for example, will make a mistake on this example here. x1 is 0, all the other things are there, f and h will disagree. Why? Because this x1 does not show up in this example. So there is some literal. A literal is a feature, a Boolean variable, or its negation. There is some literal x, in this case x1, there's some literal z, which is there which is present in the true function, but not, which is present in the hypothesis, but not the true function. Like x1, this is a bad literal. This is the kind of literal that we know is going to hurt us. So if x1 does not appear in an example, and 2, 3, 4, 5 and 100 appear, the true function will say it's positive. Why? Because x2, the true function is simply going to say yes if 2 and 3 and 4 and 5 and 100 are present. But the hypothesis not only wants these 5 things to be present, but also an additional thing. But that's going to give us a mistake. The opposite case can never happen. Because this is a conjunction, this is just in this special case. And the visual thing is something like this. The true function predicts a set of points as positive, and any hypothesis that has been chosen on the training set, because of the nature of the elimination algorithm, is going to necessarily find a subset of it. Questions? This is important because we're going to use this fact that the true function, the hypothesis will never make mistakes on negative examples to be able to derive the guarantee that we'll get. Okay, so what's the guarantee that you can get? So let's analyze this function. I'm going to, in the spirit of scaring you, I'm going to throw out some math.
Oh my gosh!
I know. So we can state the following theorem. Look, if we are learning this function using the elimination algorithm, then suppose you have a certain number of training examples. I'll use the letter m throughout this section to denote the number of training examples we have. If we have m training examples, and that number, the number of training examples, is greater than some quantity here, it doesn't matter what the quantity is, it's greater than that quantity, then with high probability, with probability greater than 1 minus delta, the classifier that you learn will have an error that is very low. The classifier that you learn will have a true error, the generalization error, that is less than another small number that's called epsilon. The English version of this is, if you have these many training examples, the algorithm, the learning algorithm, the conjunction, the elimination algorithm will produce a function that with high probability will not make too many errors. The way to interpret this kind of statement is to start filling in numbers. So, how do you use this? Suppose, think of this as epsilon is the error that we care about, that we want to guarantee. So you have a procedure that manufactures, I don't know, some toys, and you want to guarantee that the toy is not going to be defective. With the number of mistakes, the errors in the defects is epsilon. And you want to give a guarantee that your manufacturing procedure will make good toys, meaning the toys with high probability, your manufacturing procedure will make good toys. So if your error that you care about, that you can live with, is say 0.1, and you want this confidence of 0.9, so delta is 0.1 as well, then just plugging in these numbers, if you, n is the dimensionality, that's always, that tags along all the time. For 100 dimensional functions, which is what we had before, for 100 dimensional functions, if you have, you need at least 6,908 examples to get to get a classifier with this guarantee. If you reduce the dimensionality, if your dimensionality goes down to 10, then plugging in those numbers with the same guarantee, you only need about 500 examples.
So, something that I've been wondering, maybe throughout this entire class, like even with that O of N notation, does N mean data set size or
So here,
dimensionality?
on this slide, N is a dimensionality. So it's an n-dimensional Boolean example.
Okay.
M is the number of training examples. In this case, there are no consistent notations. For this slide, this section, I'll try to use M consistently to represent the number of training examples that you have. And just, yes?
So is it essentially the Chernoff bound?
It is the Chernoff. In fact, this will get, to prove this, we will use something like the Chernoff bound. In fact, the Chernoff bound occupies a, we'll get to the Chernoff bound later, so yes. Another, another point, if say you have 10-dimensional examples and we still want a classifier that gets 90% accuracy, meaning the error is 0.1, but we want a very high confidence on the statement that I will produce a classifier with error 0.1. We want confidence of 0.99. Then you need way more examples. You need 700 examples. Yes.
Just a quick question. This is law-based too because it's a binary whether they have error or not, right?
Yep.
Okay.
Yep. The multi-class or the generalizations kind of have a same flavor, but you have to redefine the idea of an error. So the two important concepts that we had, one is the definition of error is crucial, and the second one is IID.
Does this theorem just apply to elimination?
To what?
Elimination?
This is only for this particular thing is only for elimination. We'll generalize this to arbitrary functions later, but given that we have 10 minutes, I'm going to walk you through the proof. So let's prove this thing. It's not the most trivial proof around, but it's kind of interesting. So I'm going to define this quantity P of Z. It's the probability that for a positive example, some feature is absent. Some feature, any feature. So if the feature is relevant, it's in the true function, then for every positive example, by definition of conjunction, that feature should be present. So for all relevant features, P of Z is 0. For irrelevant features like the x1, we are asking what is the probability that x1, this bad literal that we had, shows up with positive examples. Okay? Now, this is an interesting quantity partly because we know we are going to only make mistakes on positive examples in the future. And so, it's these literals with non-zero P of z that can probably hurt us. Okay? So, let's now look at redefine this quantity, the generalization error that we had in terms of this P of z. And I'm going to claim that the error that any function can possibly have in over the true distribution is less than the sum of all the P of z for the variables in that function. So, for example, our original function was, the function that we learned was x1 and x2 and x3, x4, x5 and x100, and I'm going to claim that the error of that function is less than or equal to the P of x1 plus P of x2 plus P of x3, x4, x5, x100. And we know that for 2, 3, 4, 5 and 100 P of z is 0 because they are in the conjunction. So really the error of that function is simply less than P of x1. Now the reason for this less than this inequality is the union bound. You might have seen the union bound in your introductory probability class, but let me just remind you, it's just saying that you have a collection of events. The probability that of any of those events happening is less than the sum of the individual probabilities. And this is one of the most important tools that we'll consistently keep using. You have, let's say you have two things, event 1 and event 2, the probability of either event 1 happening or event 2 happening is less than the probability of event 1 happening plus the probability of event 2 happening. Questions? Right, so now if there are no questions, then let's start proving this thing. I'm going to call a literal, I'm going to define a literal to be a bad literal if its probability, if P of z for that literal is high. It's more than some value, some epsilon over n. What does this mean? Intuitively, like x1 is a bad literal if it has a high probability of occurring with a positive example. And the reason for this is because if it occurs with all positive examples in the training set, then, sorry, did I say high probability of occurring with a positive example, high probability of not occurring with a positive example. So x1, let me come back to this. x1 is a bad literal if it has a high probability of not showing up with a positive example. So x1 does not show up with a positive example with probability P of z. And we've generated this training set and we keep sampling examples, and if the entire training example, if it showed up with a positive example every time, then it has really violated this thing. It has gone against this, the probability that it shows up with positive examples is really 1 minus this. So if there are no bad literals, if we do not have any bad literals, then we are okay. The error has to be less than epsilon because we know that the error is less than the sum of P of z, and P of z is less than epsilon over n. There are only n literals, so this is okay. The interesting situation is when there are bad literals, like the x1 that we had. So if there are bad literals, let's pick one of them, some bad literal. This x1, that shows up, that does not show up with positive examples in general. And let's ask, what is the probability that it doesn't get eliminated by one example? What does it mean to get eliminated by one example? It means that there is one positive example where this feature did not appear, because that's the proof that this guy is not in the conjunction. So the probability that this feature does not get eliminated by one example is simply 1 minus the probability that it gets eliminated by one example. The probability that it gets eliminated by one example is the probability that this particular feature does not show up. It does not show up with a positive example. But we know that that value is more than epsilon, so this quantity, probability that this literal survives one example has to be less than 1 minus epsilon over n. This is okay? Questions?
Can you walk through that logic?
So this quantity P of z is the probability that some literal appears with a positive example. I keep saying that the wrong way. There is this the probability that a feature does not appear with a positive example is P of z. Okay? If a feature does not appear with a positive example, it gets eliminated. So the probability that a feature will get eliminated by some example is 1 minus P of z. Sorry, it's simply P of z. The probability that a feature does not appear, let me walk through this again. If a feature does not appear with a positive example, it gets eliminated. The probability that the feature does not appear is P of z. So the probability that an example will eliminate it is P of z. The probability that an example will not eliminate is 1 minus P of z. Right? And we have made an assumption that P of z is more than epsilon over n, we just plug that in. So the probability that any one example will not eliminate this feature is less than 1 minus epsilon over n. Intuitively what this means is that there's this bad literal that can potentially give us trouble in the future, and we are trying to upper bound the probability that it will survive. Probability that it survives one example, then we'll get to the probability that it survives two examples, which is just the product, it survives the entire training set, and that gives us your bound. So, since I have 2 minutes, I think I can complete the proof. What we know is probability that a bad literal survives one example has to be less than 1 minus epsilon over n. And as I said, we have m examples. Each of them, this is where the IID assumption comes in, each of them is independent of each other. So the probability that it survives 2 examples is that quantity square. Probability it survives 3 examples is that quantity cubed. The probability that it survives m examples is 1 minus epsilon over m. This is for one feature, a particular feature called z. The probability that not even one such, probability that any of these bad literals survive, we have the dimensionality is n, so we have n such things, we just add them up. This is another application of the union bound again. We have 2 events that are happening, the probability that any of those 2 happens is simply less than the sum of those 2 things happen, sum of the probabilities. So the probability that any bad literal survives is less than n times that quantity. Okay? I think we're almost done with the proof, because what we want is that quantity to be small. The probability that any example survives or any bad literal survives, like the probability that x1 survived the entire training set, we want it to be small. So we want to put an upper bound on that right hand side. So in particular we'll say that what will happen if that probability, or let's demand that this error happens with probability less than delta. So we are going to say that quantity on top, we are going to demand that it's less than delta. If that is the case, then we are okay if delta is small, because the probability that we will make an error has to be less than n times blah blah blah, and if that quantity is less than delta, and if delta is small, then the probability we'll make an error is small. And now we are a minute over time, so I'm going to continue on this early in the next class. But I encourage you to go back and look at this proof because it's not trivial, and yet it's basically the style of proof that we continuously keep doing.